Hello, Steve here again. Welcome to week 6A. So we had the midterm this week, but according to the tentative syllabus, combinatorics is supposed to start in week 7, so we're a little bit ahead. We're going to spend most of our time next week doing the remainder of chapter 6, but let's just do section 6.1 today, please. So let us try and toggle. Over to here. There we go. So this is the slides already posted. All of the chapter 6 slides are posted already on Canvas. So I don't know, maybe some of you may recognize that. That's Pascal's triangle. Of course, it goes back to ancient times. So this is where we are right now. I'll be giving you the third assignment, next week or so. We have another midterm coming up, and what is it now? It's just 1, 2, 3 more weeks. We have a midterm that'll cover these topics all the way up to functions and relations. Try and have a gap there, give you a bit of breathing room to review for it, because of course this course does go fairly fast. We may not do formal languages. It depends. It looks like we can, but that's usually it should be there. You should learn it. And it's just for the past 10 or 15 years, it's been out of the syllabus. Now they're trying to put it back in. So there you have it. So here's the chapter, the parts that we're going to cover. Okay, this is generalized permutations, combinations, generating permutations, combinations. That's later. Right now, we're just going to stick with these basics up to the binomial theorem. So, basics of counting. So typically, combinatorics deals with finite structures such as graphs. You're used to graphs of a continuous function. Here we talk about discrete graphs. Hypergraphs, which are graphs in higher dimensions. Partitions, I think we already talked about what a partition is in set theory. And partially ordered sets. Of course, partially ordered sets. That has to do with the Cartesian product. So rather than the object itself being the study, what characterizes combinatorics are its methods: counting, arguments, induction, inclusion, exclusion, and we're not doing the probabilistic method. That's for Compute 210. In general, surprising applications of relatively elementary tool results rather than gradually developing a sophisticated formal machinery. So just like the rest of this course, we pull in all these different discrete subjects and put them together under one textbook. So we're going to begin with this idea of enumeration. So the fundamental topics are rule of sum, rule of difference, rule of division, the multinomial coefficient formula, and the rule of product. Combinations with repetition, most of this is without repetition, and then distributions, which is just a carry on from combinations with repetition. Well, it generalizes what we've done before in the guise of boxes and containers, being unique and non-unique both ways. So there's 4 possible combinations. So enumeration, to count off by name, one by one, no big deal, just like here. This is the enrollment of this class, and I can see I'm enumerating the number of students. Clearly, this is consistent because the labs add up to the number of people in the labs add up to the total people in the class. Here, let's look at my SFU ID. So the first 2 digits indicate the year I entered the system. That might be a bit scary. So how many unique IDs can we make per 2-digit year? Of course, that could have went down the pipe at Y2K, which was the rollover of the millennium back 26 years ago. So there's 1, 2, 3, 4, 5, 6, 7. Okay, so that can have 10 possibilities, times that can have 10 possibilities, and so on and so on. So that's 10 to the 7. All right, 10 to the 7 possible unique IDs. So 10 million students can come to SFU per year. Okay. So how about this license plate, DHK 594? So how many license plates are possible given 3 uppercase alphabet letters and 3 numeric letters? So here are the other possibles right here. Look at them. They're all these different possible. Well, it's 26 times 26 times 26 times 10 times 10 times 10. So with non-repeating characters, well, that's different. Now, we pick one of these, that's 26 possibilities. Now I've taken one out of the alphabet, so that leaves one less, that's 25, and one less again, that's 24, and the same holds for the numerics. 10 by 9 by 8. So that's how we reason in counting. How many arrangements are there for the letters D, H, and K? Here, look, 1, 2, 3, 4, 5, 6. You can do that in your head, but we'll find out a way to actually calculate that. There's a formula for it. It's simply 3 factorial, as it turns out. So let's just now, that was an introduction, let's talk about fundamental principles. So we begin with the simplest, the rule of sum, and that has to do with 2 disjoint sets, okay? Okay, stated simply, it is the idea that if we have 8 ways to do something and B ways to do another thing, then we cannot do them both at the same time, then the rule of sum says that the total number of ways to choose actions is the sum of both individual ones. You can think of it like that's the generalized rule of sum. So it's not just two sets, it can go on to n sets. That's no big deal. So that's just the cardinality of all these individual sets is simply the cardinality of the union of all those sets, is it not? That's pretty simple. So here, for example, when you think of rule of sum, think of sequential loops, not nested loops, sequential loops. Okay, so what is it here? Well, what does it determine the value of the integer variable counter after executing the following program segment? Here, I, j, and k are integer variables. Well, this has to go first. That's 1 to 12. So it's 12 cycles. Then j has to go next. That's going to be 5 to 10, 6 cycles. And 15 down to 8, well, that's 8 cycles again. So it is 12 times 1 plus 6 times 2 times 8 times 3 as far as the counter is concerned. You can see the plus 1, plus 2, plus 3, right? Okay. So the formal rule of sum is like we've just stated. There it is. I don't know why I've stated it again. Maybe I should take it out. Okay, but it deals with disjoint sets. That's the key. But now we're going to talk about the rule of subtraction, which is really inclusion, exclusion, which we've already seen. And this one's different. This is when you have non-disjoint sets. There's overlap. And so you're overcounting in the intersection, as we saw before. So here we don't just have 2 simple disjoint sets. Here we have 2 sets such that their intersection is not the empty set. Okay, so here we add all of this, then we add all of this, and you see we twice counted the intersection, so we have to get that out. So that's the principle of inclusion exclusion. How many a computer company receives 350 applications from college graduates for a job planning a line of new web servers? Is that all we do with computers today? Suppose that 220 of these applicants majored in computing science, 147 majored in business, and 51 majored in both computer science and business. I smell inclusion exclusion coming. And so how many applicants majored in neither computer science nor business? So, I mean, here it is. That's the, we want the cardinality of the union of A1 and A2. And so we call that U, all right, minus the intersection, okay? So this is defined as, well, this is like the universe, okay? The complement of that. Here's U out here. So it's U, the complement of A union B, okay, equals U minus this part right here minus the whole thing, all right? Which is the sum of A1 and A2 and of A3, but we have to take that twice counted part out. So when you plug the numbers in, you get this 34. Now, please be able to do this, be able to do a problem like this for up to 5 sets. Okay, I'm giving you a hint on the final exam. There's a question like that on the final. As you can see, if you pay close attention, you should have learned from the midterm, those of you that are, that there was a nothing on the midterm that we hadn't discussed before, that I hadn't alluded to before, that I hadn't stated this will be on the midterm. So if you pay close attention, you get 100% in this course quite easily because you have time to work things out. All right. Not only that, you have the great tutor, ChatGPT, but I have to warn you, it makes a lot of errors. But that's good for you because it means you have to think. It means you have to check its answer. If you have trouble coming up with an idea and you don't want to waste too much time because you're close to the edge, do ask it. That's a good idea. It helps you. It's like working with a partner. And we do that normally, so there's nothing wrong with it. But don't trust it. I kind of look at ChatGPT as a kind of a really incredibly intelligent Renaissance-like person, but slightly mentally ill. That's the way I look at it. All right, so let's just move on. The formal rule of sum and subtraction is generalized as such. So what do we have here? The inclusion exclusion principle, we thought about generalization of the rule of sum, and that it too enumerates the number of elements in the union of some sets, but does not require the sets to be disjoint. So here we have it. This is the general form of the inclusion exclusion principle for n sets. Put 5 in there and see what comes up, just so you're prepared for the final exam. So counting bit streams is an easy way to see it. So for example, what's it doing that? So how many bit strings of length 8 or either start with a 1 bit or end with 2 0 bits? Okay, so we can see that out of all the 8-bit strings that start with 1, there's 2 to the 7 equals 128 ways. Okay, 2 to the 7 by the product rule. And 10 of those, 10 of those, 10 of those, 10 times 10 all the way to 10 to this, or sorry, 2 because it's a bit. So it's 2 to the 7 times 2 to the 7 all the way up to that. Now, if it ends with 2 zeros, well, you're taking these 2 out, so you've got 2 to the 6 ways. So to answer this question, then, they are of length 8. Either start with 1 or end with 2 bits, meaning you can't include this either. You got to take it out. There's 2 to the 5 of those, and so you end up having 128 plus 64 minus 32. That one plus that one minus that one. That's inclusion exclusion to counting bit strings. Rule of product. Statement: if a task can be done in counting bit strings. Yeah, that's fine. That makes sense, right? Yeah, that works. So rule of product. So if you have one task like rule of addition, if you have one task that can be done m ways, and another task that can be done in n ways, but they are not disjoint sets. They're related to each other. Every time you execute m, it affects the execution of n. And so doing both tasks basically the total number of ways to do both tasks in sequence is m times n. And here the canonical example, creating a secure 4-digit PIN code. Well, it's 10 times 10 times 10 times 10 is 10 to the 4, clearly. And that's the product rule, which you might say, didn't we use that here? Well, yes, we did, but we did it in the guise of the exclusion principle, inclusion exclusion principle. Here, there is 256 permutations of an 8-bit string, which is the basis of ASCII and Unicode, in fact, which is the real accepted standard. Well, at least it used to be. Things change so fast I can't keep up. So you can see the ASCII, the hexadecimal, the octal, and the binary, which we are not going to learn here. That's in a more elementary programming course, the representation of numbers, of integers. But you can see how we can just and octal and hexadecimal are very much related to binary. So there's the binary, it's right there. There's the binary, and hexadecimal is very good, for example, because it relates directly to binary in terms of representing memory locations. And octal has its uses as well because of its close, very easily translatable identity with with binary, okay, with pure binary. Okay, so 8 bits is 1 byte, and so there's 2 to the 8. That's 256 possible entries, and that covers everything in the English language. The uppercase, lowercase numbers, and the well, all the symbols in the English language. So if we had this kind of thing, ASCII for Chinese, for example, or Mandarin, you'd have to have 11-bit string, right, to represent more than 2,000 characters. So here's the best way of looking at the rule of product in terms of do loops or for loops. They're nested for loops. Okay, so I'm going to do this exercise. So at 1, oops, I got to go to J, start at 5, oops, got to go to K, start at 15, satisfy that, go to 2 here, or to 6, satisfy that, go to all the way up to 10, then I can go back to 2 up here. Then I do this again, and the same way I did before, and then I'm ready to go back to 3 up here. That is the rule of product. So this is 12 times 5 is 6, and 15 down to 8. 12 times 6 times 8. Yes. And that's just producing this I minus j times k. So that's kind of what you get there. Counting functions. Oh, well, we haven't even talked about functions as is done in chapter 3 because it's supposed to be in chapter 9. But, oh, why is it not here? I did make a change, and it's just not there. A function is a mapping from A to B, in which every element, in discrete sense, in set theory, every element of A is projected into the codomain, from the domain to the codomain, exactly once. Exactly once. That's what a function is. It's a ordered pair, like the two-dimensional plane R2. But every element in the domain is mapped exactly once to every element, or to elements in the codomain, but it doesn't have to be every element there. Otherwise, that would be a one-to-one function. It goes back and forth. They're invertible, that type of thing. But here, we can see how it works. It's pretty easy. You've got to be able to map from all of these points in set A and map over to these right here. So what is just the cardinalities n to the m? It's just like the problems we did before. There's n here. Okay, a function corresponds to a choice of n elements in the codomain. That's right there, the codomain. For each of the m elements of the domain, yes. Hence, by the rule of product, there are n times n times n times n to the m functions, because each one of these has to map exactly once to elements over here. For example, there are 5 cubed equals 125 different functions from a set with 3 elements. See, 3 elements to a set with 5 elements, okay? So I hope that makes sense. N to the m, we've seen this already before, like 2 to the m and all that kind of thing. So here, we have n of these over here that's mapped from exactly m of these. That's how this works. What's that saying? It's saying that each of these elements in the domain has to be mapped from exactly once. You don't see double arrows coming out. It's just one arrow from each of the elements and the m elements in the domain. So it is n to the m, clearly by the rule of product. One-to-one function, well, that means you have the same number of elements. Remember that a function has to be mapped from each element from the domain exactly once. So that means that it maps to exactly the same number of elements in the codomain. And so each element A is mapped to a unique element in B. Therefore, there are m ways to map the first elements of A, m minus ways to map the second. And so it ends up being this thing right here, this set of products, right? Because that's what you're doing all the way through to m. All these, which you can think of as going to 1, and then the m minus n all the way to 1 terms can cancel off with this denominator, so you only have to look at this part right here. So m times m minus 1 times m minus 2 all the way to m minus n plus 1 all the way to 2 times 1, okay? So all that's missing here is represented by m minus n factorial. So this is a much simpler formula than just showing all of these, all the way down to m minus n plus 1. There is no easy way to state that just with a factorial by itself, so you have to have this division involved as well. Here, this is an interesting problem. This is Morse code. So this problem in enumerator requires both rule of sum and rule of product, because why? Let's look at it. First of all, there's 2 elements here. There's 4 elements here. 4, 3, 1. Okay, so they're all these elements that come in different sizes. Okay, they come in different sizes. They have to be grouped according to size in order to apply the rule of product to, say, the first set, which is, well, how many are there? There's 1. 1 apparently. There's just 1. E is the only single element set. Then there's 2. Well, let's just have a look. Oh, well, anyway, then you sum up the group with 2. You sum up the group with 3 terms, and then you sum with the group of 4 elements. I don't think there's a 5 element one there. 2 5 element one. So that is how you do this. That's for you to figure out, but you have to apply the rule of product to each of the subsets of this problem. The subset with 1 element, the subset with 2 elements, the subset with 3 elements, 4 elements and 5 elements. They are summed up, but each of those elements, you apply the product rule. I hope that makes sense to people. There's also the rule of division, but this is largely used for circular permutations, although we haven't even talked about permutations yet, but you know what a permutation is. So, well, if set A can be partitioned into disjoint subsets of equal size corresponding to elements of set B, okay, then the cardinality of B equals the cardinality of A divided by K, or this form right here. So where A is the total number of arrangements or objects, B is the total number of distinct outcomes after accounting for symmetry or redundancy, say circular symmetry, K is the number of times each distinct outcome is counted. So here's a good example. Counting the number of distinct ways to seat 3 people in a circle. Clearly, that's how you apply the rule of division. Okay, so all linear arrangements are ABC, ACB, BAC, BCA, CAB, CBA. That's 3 factorial. 1, 2, 3, 4, 5, 6. But then you divide by K, which is 3, because there are only 3 people, and the reason why is because you have rotational symmetry. I hope that makes sense. So ABC, BCA, CAB, now that is the number of distinct ways to seat 3 people in a circle. Multinomial coefficient formula. So there are, and this is easy to figure out once you see it. There are n objects. If there are n objects with n1 indistinguishable objects of the first type, n2 of the second, and so forth, then there are n factorial over the product of all those individual objects factorialed, linear arrangements, of the n given objects. So here's an example. I've got Mississauga. And there's 1 M, there's 2 3A's, there's 3 S's, all right, and the rest are 1. And so here I've got n factorial, which is the number of elements, that's 10. And then there are these subsets. So M is 1 factorial, A is 3 factorial, S is 3 factorial, A is 4 factorial. You see how it works? Possible arrangements among these: 7 factorial divided by 3 factorial, 1 equals 840, in which all 4 A's are together. So you just now have produced a situation where you look at the A's as a single character, the four A's together as a single character, and therefore now you're dealing just with 7 items to arrange. Does that make sense? So this one symbol, it's asking once again, among these, there are that many arrangements in which all 4 A's are together. So you've taken A not by itself, but all 4 A's as one symbol. Therefore, instead of 10 factorial, we are down to 7 factorial. Okay, so that makes perfect sense. I hope it does to you. Here's a really nice problem. So this is the problem of how many ways are there to go from one point, say here it is xy 2 1 to xy 7 4, and all you can do is go up or to the left. So here are 2 examples. So this one is right, up, right, right, up, right, right, up. This one is up, right, 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 up, up, right, right. Okay. Well, this is another problem just like this right here. And so what do you have? You have, just to make a simple story shorter. 1, 2, 3, 4. There are 5 R's, 1, 2, 3, and 3 U's. And so it's 8 factorial, which is the total number of moves. 1, 2, 3, 4, 5, 6, 7, 8, right? Same thing here. Over 3 divided by 5 factorial times 3 factorial. So this graph problem is something I want you to know. So it's the standard application of the multinomial formula. Okay, now we have the pigeonhole principle, which you'll see maybe in some courses, like in probability, you'll see it again. It's important. It's important, but I've not used it in my professional life. Well, that's because I do mostly continuous math. So if there are more pigeons than holes, some holes have at least 2 pigeons. It's obvious. So formally, if the cardinality of set A is greater than the cardinality of set B, then for every function, a function is a relation that is defined for every element in its domain, as we said before. The mapping from A to B, from the mapping, there exists distinct A1, A2 that are in A with f of A1 equaling to f of A2. An example, you have a drawer containing socks of 3 colors, red, green, blue. How many socks must you pick to guarantee that at least 2 have the same color? Obviously 4, because it could be possible that you've picked all 3 colors. So that's the guarantee, is that just one more sock is all it takes to have a pair of the same color. So this is the first step beyond the introductory rules of combinatorics and states very simply that if n items are put into m containers with there at least one container must contain them. I don't know why I said this twice. Oh, well, yes, okay. This should come before the other slide. This should have come before this one, I think so. No, that's all right. I should just take that slide out. Okay, yeah, I'll take that slide out. The pigeonhole principle, you can generalize it here. For example, if a flock of 20 pigeons roosts in a set of 19 pigeonholes, one of the pigeonholes must have more than one pigeon. So the principle is if k is a positive integer and k plus 1 objects are placed in k boxes, then at least one box contains 2. Proof, why do we have to prove this? It's so almost self-evident, but we use the proof by contraposition. The contrapositive. Suppose none of the k boxes has more than one object. Then the total number of objects would be at least k. This contradicts the statement that we have k plus 1 objects. This proof is wrong. It is proof by this is proof by contradiction, not proof by contraposition. Bad, Rosen. This is from Rosen. Okay, pigeonhole principle among any group of, this is called the birthday paradox. This is wonderful. The birthday paradox, something you should know. Among any group of 367 people, remember there's 365 days in the year, there must be at least 2 with the same birthday because there are only 366 possible birthdays. Oh, okay. So not 365, 366 when you include February leap year. So show that for every integer n, there is a multiple of n that has only zeros and ones in its decimal expansion. Solution: let n be a positive integer. Consider the n plus 1 integers all the way up to here, where the last has n plus 1 ones. There are n possible remainders when an integer is divided by n, right? So by the pigeonhole principle, when each of the n plus 1 integers is divided by n, at least 2 must have the same remainder. Subtract the smaller from the larger, and the result is a multiple of n that has only zeros and ones in its decimal expansion. I want you to study this and understand what I just said. To teach this like this is, well, let's just say it's demanding. Oh, hello back again. I just had to make sure that I was telling you the right thing. That last example that I showed you, that involves the pigeonhole principle. It is the pigeonhole principle, but it is related just by going into probability theory, which we're doing this course, as the birthday paradox. So I said this was the birthday paradox. That I knew that wasn't right. I had to make sure. And yes, that has to do with probability. So taking this one step further into probability would make that so. I just want you to understand this particular pigeonhole principle problem. So generalized pigeonhole principle. Okay, first of all, we have to define two new functions. The floor function and the ceiling function. Basically, this is a round down and this is a round up function. So here you can see the symbols, a bracket like this, okay? And it's the max of n such that n is less than or equal to x. So if I put 3.7, the floor function is 3. Minus 1 by 2, back down the number line to minus 2. The ceiling function does the opposite. So the ceiling function of 3.7 rounds up to 4. Minus 1 by 2 goes to minus 1. All right? So knowing these functions, we can now just present this generalized proof of the pigeonhole principle. So if n objects are placed in k boxes, then there is at least one box containing at least n over k objects. So this is the generalized pigeonhole principle, not just one or two missing. This is more general, okay? N objects arbitrary, k boxes arbitrary. The proof is by contraposition. Again, what's wrong with Rosen? It is not. It's contradiction. Anyway, so suppose that none of the boxes contain more than n over k floor function minus 1 objects, okay? We have to use the floor function because the fraction doesn't produce integers generally. It's always, the floor function produces fractions or decimals without the decimal. Anyway, then the total number of objects is at most, according to the pigeonhole principle up here, k times n over k minus 1, which is less than k times n over k plus 1 minus 1, which equals n if you factor out all the terms here, where the inequality ceiling n over k is less than ceiling n over k plus 1 has been used. That's the inequality. This is a contradiction because there are a total of n objects. So for example, 100 people, there are at least 100, ceiling function 100 over 12 equals 9, who were born in the same month. So this is a very, very good problem. You have to know the generalized pigeonhole principle. You have to know how to apply it. For example, this example. I'm not going to ask you to prove it, though, because I haven't spent very much time at all, if not any, on floor and ceiling functions, which I've sort of moved away from since I've moved functions up to chapter 9. So you don't have to know ceiling and floor functions. Therefore, you don't have to know this proof. Okay. Generalized pigeonhole principle. So how many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suit are chosen? How many must be selected to guarantee that at least 3 hearts are selected? So these are good. We assume 4 boxes, 1 for each suit, right? It's um, clubs, diamonds, hearts, spades. Using the generalized pigeonhole principle, at least one box contains at least n over 4, that's 4 over 4 cards, at least 3 cards of one suit are selected if n over 4 is greater than or equal to 3, obviously, by the definition that we have up here. The smallest integer n such that the ceiling of n over 4 is greater than 3 is n, which equals 2 times 4 plus 1, which is 9. Okay, so that's how many cards to select to guarantee that at least 3 cards are from the same suit. I mean, it's a trivial application. Now, how about at least 3 hearts? Okay, so a deck contains, by the way, these problems can be done with combinatorics, much easier than using the pigeonhole principle. These kinds of problems, calculating the probabilities of suits. That's why I don't generally go too far into the pigeonhole principle, but it's important for 210, for probability theory, so I spend a little more time on it now than I did before that course was invented. So a deck contains 13 hearts. It contains 13 of each suit. 4 times 13 is 52. Which are not hearts, along with 2 hearts, okay? We may have 39, so if we select 41 cards, right? That's 52 minus 13 hearts and 39 cards, 39, 49, 55, 52, that's right. So if we select 41 cards, where'd 41 come from? Oh, okay. So if we select 41 cards, we may have 39 cards which are not hearts along with 2 hearts. 49, 41, that's 39, 40, 41. 3, there's 3 cards. Okay, a deck contains 13 hearts, 39 cards, yes, which are not hearts. And what do we want here? At least 3 hearts are selected, so that's how we get to 41. However, when we select 42 cards, we must have at least 3 hearts. Note that the generalized pigeonhole principle is not used here. Well, that solves that problem, I suppose. 42 cards, we must have at least 3 hearts. So that's the answer right there. So permutations, combinations. All right, so this is something I think most of you have already seen before, hopefully. There's combinations and permutations without repetition and with repetition. So if we want to take combinations like we have A, B, C, D, then combinations mean I choose them, but they're still in that order. A, B, C, D. Here I have A, B, C, A, B, D, A, C, D, B, C, D. So I'm not permuting them, I'm just choosing them. Different combinations of those 3 elements where they stay in their first, second, and third slots. The formula for evaluating this is for taking 3 at a time. Well, it's and this is the notation. Are combinations of n objects, which is n factorial over r factorial n minus r factorial. How do we derive at that? Well, I think we've derived part of it already. We've derived the permutations, which is n factorial over n minus r factorial. We already saw that earlier, and we didn't call it a permutation, but that's what it was. But here, when you divide in r factorial, then you get the combinations. So combinations with repetition. Here, combinations with, this is without repetition, this is with repetition. So A, B, B, A, C, C, A, D, D. So they're still chosen in order, A, B, C, D, but now you can have repetition. Before, you couldn't have repetition, simply 4 factorial. Here, well, it's this funny thing that we're going to discover next week. It's a different kind of combination. I call it C prime, R choose N. N choose R, which is this new formula, slightly augmented. We'll derive that. For now, just accept that you can see from 4 characters A, B, C, D that here are, without repetition, the combinations. Here are the same combinations, but with repetition. Then each of these combinations can be permuted by the rule of product. That's just imagine the permutations of all these. I've got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 of them. Here I have 64 altogether, where I take each of these and I permute them. That has no permutations. This has several permutations. This does. You get the idea. But the number of permutations with repetition of n objects is just simply n to the r. Okay, we've seen this already. Like bytes are 2 to the 8. 2 to the 8 bits make a byte. Okay, 2 to the n bits are a byte. So that's n objects taken r at a time. N objects taken r at a time. This was n objects taken r at a time, chose r at a time. This is taken r at a time. So permutations, repetition, combinations, or distributions. Combinations with repetition, but here you see this word distribution. That comes later. We find out that combination of repetition is related to distributions. That's the last chapter that we will study in this, in chapter 6, the last section. Okay, so we've covered that. So combinations, how many ways are there to select 5 players from a 10-member tennis team to make a trip to a match at another school? So by this theorem, the number of combinations is 10 choose 5. 10 members, 5 players, so it's 10 factorial over 5 factorial, 5 factorial using this formula right here. 10 factorial, 5 factorial, 10 minus 5 is 5 factorial. Okay, you see that? See how that works? And when it comes to exams, you only have to go that far. You don't have to expand the factorials, Art. That's ridiculous. A group of 30 people have been trained as astronauts to go on the first mission to Mars. How many ways are there to select a crew of 6 people to go on this mission? 30 people, 6, well, it's 30, choose 6. It's obvious what it is, okay? Now, you don't have to do all this. You just have to leave it at that form right there. Here's a really good one. It's one of my favorites. This is Braille. So these are raised dots. There's no raised dots here. And so how many different symbols can you represent in the Braille system? Well, there's 6. Okay, 2 to the 6. It's binary. It's either raised or not, so that's binary. So there's 6 of them, so it's 2 to the 6. 2 to the 6 minus 1, because this one you can't feel anything. How many symbols have exactly 3 raised dots? Well, that's 6 choose 3. And how many have exactly even numbers? 6 choose 2, plus 6 choose 4, plus 6 choose 6, which is 31. So that's how you apply combinations without repetition. Didn't I just do this one? Somehow I got to this one. I have no idea what just happened there. How did I skip ahead like that? Okay, that shouldn't be there. Good God, what the heck? How did I make that mistake? All right, okay, fine. More mistakes. Binomial coefficients and identities. Okay, I'm going to go through this quickly. I'm not going to derive these things on paper. I'm going to do it next week because I don't want to go past hour and 15 on this for obvious reasons. So section summary, we've done what we're going to do is combinatorial proofs, the binomial theorem, Pascal's identity, and Pascal's triangle, other identities involving binomial coefficients. And note, we've introduced an alternative notation now. We use this notation here instead of this. So this is a binomial coefficient. This is just simply n choose r. Combinations without repetition. And we represent a binomial coefficient like this. In fact, I think I'll start this afresh so that I actually do write these things out. Let me just leave this presentation for now, come back to it maybe tomorrow or so. But everything will be posted by the end of next week, by the beginning of next week, actually. So we're sort of ahead of schedule right now anyway. I believe it's time to take a break. All right. So, okay, it was nice seeing you all on Monday, and I'm really looking forward to those exam results. I really hope and pray, if I did such a thing, that you did really well. I certainly hope you did. I'm rooting for you. Anyway, until we find out what it is, it'll be by Monday. You'll find out what your scores are. Take care. Have a good weekend, and goodbye.